So now the question is, now that we have this really like useful unit or unitless measure of rotation, how do we convert from degrees to radians? So let me write that out. So convert from ... and we'll go both ways. So degrees to radians, degrees to radians. This is what you would do. So let's say you have X number of degrees, okay? So just some number of degrees that we have, and we want to convert it into radians. So the thing is, what we're going to do here is this X degrees is kind of like over 1, because when you just see something, it's automatically kind of divided by 1, right? And what we want to do is kind of get rid of this degrees. So we want to divide by that unit and kind of tack on something radians, right? So the thing is, we could use the ratio for a full circle, right? Because we said a full circle is 360 degrees, and a full circle is 2 pi radians, right? And this thing here, this second thing that I'm drawing in parentheses, this is called a conversion factor, right? You might have seen this in classes like chemistry or other kinds of sciences or math classes, right? So anyways, the thing is here, though, we can always just cancel out this 2 and the 360 and reduce it to pi over 180, right? And that's usually what we see is X degrees or whatever it is, okay? And then times pi over 180 degrees, right? And we don't have to write that radians because radians are technically a unitless measure. And the reason for that is actually because of the last slide. Remember we said S over R? That's what a radian is. That tells us our radian measure. And S is an arc length, and radius is also a unit of length. So when you divide, let's say, I don't know, feet by feet, you just get nothing, right? There's no more units there. So that's why a radian is unitless. Anyways, fun fact there. So the thing is, when you want to convert from degrees to radians, you just multiply by this conversion factor there, okay? And it will be exactly the opposite if you want to convert from radians to degrees, okay? So let's say you start with X radians. Okay, I'll just put radians there for the sake of showing what I'm showing here. So X radians, then you just want to flip your fraction there. So now you want to have radians on the bottom, so pi on the bottom, and then you want to have your 180 degrees on the top. So when you want to go from radians to degrees, you just multiply by this conversion factor here. Okay, so at this point we've talked about arc length, right? So we've said that if we have a circle and of a certain radius, r, and we rotate a certain number of a certain angle, right? Then this S, this arc length created or kind of swept out, given a certain angle. Sometimes it's called subtended by an angle. Sometimes you'll see the word subtended. Okay, and the way I think of that is always it kind of means like swept out or drawn out, swept out or drawn out. Okay, so that just means created, basically, by rotating a certain angle. So S, arc length, is equal to R times theta, right? And now we're going to learn something new. So this thing here, this kind of like pie, or piece, this slice cut out, or created, this is called a sector, okay? So that whole slice there is called a sector, right? And the area of a sector, drawn out is equal to, and I'll give you guys a formula here that's pretty useful, 1/2 times theta times r squared, okay? And the important thing to note is that theta is in radians for this formula. Okay, so let's try an example of using this formula here. Alrighty, so we have a little word problem. So it says an automatic lawn sprinkler sprays a distance of 20 feet while rotating 30 degrees. What is the area of the sector of grass the sprinkler waters? So if we visualize it here, let's say we have, I don't know, sprinkler. I'm just going to draw a little square. Okay, so here's the sprinkler, and it says it sprays a distance of 20 feet. Okay, so this is like R is equal to 20. Okay, and then it says it rotates 30 degrees. So this theta is going to be 30 degrees, right? So let's say we have something like that. So what this does is it sweeps out a sector, right? And what we want to do is find the area of this guy. the area of this grass here. Okay, so we just apply our formula where A, area of a sector, is equal to 1/2 theta times r squared. But we can't, the thing is, the first step what we have to do is convert our theta equals 30, we have to convert that to radians, right? Because our formula only takes in radians, and it only works when our angle is measured in radians. So, in order to convert, we just have to use a conversion factor, and you can tell which conversion factor it's going to be, aka like pi over 180 or 180 over pi, by saying, okay, what units do we want to cancel out? And in this case, we want to cancel out degrees, so our degrees have to be on the bottom, and our radians have to be on top, right? So these are going to cancel out and give us a pi over 6, okay? And so now we have theta, our angle, in terms of radians, so that's good. So now we can just plug everything in, so we have A is equal to 1/2 times, and theta is now pi over 6, which is radians, and r is 20, and that's being squared, okay? So when we just simplify, we just get pi times 400 over a 12 here, okay? And then that's going to be, let's see, if we divide by 4 top and bottom, we just get 100 pi over 3, okay? And that's going to be, if we look at the units of what we have, of what we started with, this is radians, which are technically unitless, but we call it radians just so we know what exactly we're talking about that doesn't have a unit. It's kind of weird. Anyways, so this is unitless, so it doesn't have a unit attached to it, and this was given in feet, right? And we have feet squared, so this is going to be 100 pi over 3 feet squared, okay? And that makes sense because we have area, so that's some unit of distance squared. All right, so now to explore another topic, so now we have, let me identify what linear velocity is. So we know what velocity is, right? That's that tells you kind of like your speed and direction at the same time, okay? And linear just means we're talking about moving a certain distance, okay? Like it talks about your position, alrighty? So the formula for linear velocity is V is equal to S over T, okay? So in this case, because we're working with angles and circles and things, our S denotes our arc length, okay? So arc length means like how the distance that you travel on a circle, okay? So this is your arc length, or distance you travel on the arc, divided by time. Okay, so that means like if you were an ant on this circle for some reason, and you were like running, that would tell you how fast you're running, because that means the distance you're traveling, your arc length, divided by time, okay? Whereas there's another kind of velocity we can measure now that we're dealing with angles, and that's called, surprisingly, angular velocity, okay? And this one is denoted by this symbol here, which is actually a Greek letter, even though it looks like a W. It's called omega, okay? Omega, that's how you say it, is equal to, this is going to be theta over t, okay? And theta is just our normal angle, the angle that you rotate. Okay, so let's say we're moving from this point to this point, so theta would be this guy in between. So this is the angle we rotate, angle that we travel, divided by time. So that means this tells you how fast you're rotating. How fast you're rotating. As if you were looking, let me finish that there. Okay, so this is more or less like if you were standing here, you don't have to be an ant anymore. It could be like yourself or whatever. And you're watching this ant travel from here to here, and you're kind of following it and like pointing, I don't know, yourself toward this ant, and then you are kind of turning at the same time that they're going. That would be how fast you are turning, or how fast you are rotating on the center there, okay? Alright, so let's try an example using this new formula of angular velocity that we just learned. So, it says a water wheel completes one rotation every 5 seconds. Find the angular velocity in radians per second. Okay, ignore the little 3 there. I think that was like a subscript or superscript thing. So anyway, so a water wheel, it says it completes one rotation. So one rotation, we can write every, so that means we have some kind of ratio going on, every 5 seconds. Okay? And what we want to do now is find this in terms of some number radians per second. Okay? So the thing is, one rotation, that kind of just means one full trip around a circle, right? Which in radian terms, that kind of just translates to saying, okay, so we can use a conversion factor, right? So if we have this one rotation or one revolution, you can hear either one, over 5 seconds, we can use the conversion factor that one rotation, because we want to cancel out rotation units, right? So we put that on the bottom. So one rotation is equal to 2 pi radians, and we don't have to write radians because they're technically unitless, right? So if we cancel those out, we just get 2 pi over 5 seconds. So that tells us 2 pi over 5. We could also write 2 pi over 5, and if you really feel compelled to, you can write radians per second. And that is actually our angular velocity, right? Because we have an angle in radians divided by time, which was 5 seconds. Okay, so this is our angular velocity for this problem. Okay, and lastly, here's a useful equation to relate our linear velocity, linear and angular velocities. Okay, so the thing is, we're going to start with, let's say, v. Okay, so this is our linear velocity, and we said that's equal to distance over time. And in this case, our distance happens to be the arc length, just because we're dealing with circles and moving on a circle, right? So arc length over time. And remember, before we said arc length could be written as r times theta, right? And then over time. And let me write this, I'll break it up in an easier fashion here. So let's say this is the same exact thing. I just put one thing in parentheses and the other one just outside there. Okay, and this theta over t, remember we said that's actually our angular velocity. This is equal to omega. Okay, so this is equal to r times omega. So what does this tell us? The resulting equation that we get is v is equal to r times omega. V is our linear velocity. R is our radius, okay, and omega is our angular velocity. So this gives us a very quick way in order to relate our linear velocity to our angular velocity. All you have to do is multiply omega times r in order to get your linear velocity, and we're there, okay? Alrighty, so that wraps up our concepts video on the section on angles. I hope that helps, and I'll talk to you in the practice problems video if you watch.